Welcome to Lyons Township High School AP Physics. Today we got a short example involving rotational motion in the Rotor Ride, or at Great America there used to be a ride called the Cajun Cliffhanger. And basically it's really simple. Imagine a huge or large cylindrical room, and you stand up against the edge of the room begins to rotate about its center, and it gets going faster and faster and faster. When the room gets going fast enough, the floor drops out and you are stuck to the wall and you do not fall. So we're going to analyze that situation and, for instance, determine something like what's the minimum speed you have to go before they can drop the floor out and you not fall down. Okay. We'll also talk about the time it takes to go around real briefly. So I'll draw a real quick sketch. You've got a big cylindrical room, looks something like this, and you are plastered up against the edge. And in this view, you are, let's say, coming out of the board toward the camera, or toward you. Okay, so at this moment, you're coming out the board toward you, and you're going to go like this. Okay, like a washing machine or something. All right, so in order to analyze this situation, we need to know what forces act on the passenger. Okay, and this is the hardest part. Like, if you can draw the FBD correctly, the rest of it's actually fairly simple. But drawing the correct FBD, identifying the correct forces and which way they point, that's the hardest part. So here's the passenger. Well, what forces act on the passenger? Well, we'll start with weight. We know mg points down, so I'll just draw that in right away. That's an easy one. Okay, now the rest is a little tricky. What else is touching the passenger? Well, the wall. That's it. Okay, now the wall can provide two forces. It can provide a normal force and it can provide friction. The normal force is always perpendicular to the wall. A mistake that people will make is they'll draw a normal force up because they're just used to saying, oh, normal force points the opposite way of gravity. Well, not in this case. The wall is vertical. The normal force must be perpendicular to the wall. So the normal force is horizontal. And specifically, that passenger is trying to go straight. The whole point of circular motion is Newton's first law. Things want to go in a straight line. So that passenger is trying to go straight. We need something to press that passenger into the circle. That's the wall. That's your normal force. So your normal force actually points to the right. Okay. Now we're not done. Okay. If these were the only two forces acting on the passenger, two things would happen. They would go in the circle all right, but gravity would accelerate them down, and they would go down into a spiral and hit the floor. Okay, there's got to be an upward force holding the passengers up. Okay, and it's got to equal mg, by the way, because the passenger is not accelerating up or down. So what could that force be? What could that upward force be? Well, that force is parallel to the wall. The only force left available to us is friction. Okay, I had actually ridden on that ride many years ago when it was still at Great America, and when the floor dropped out, you felt the wall tugging up on your shirt and your pants and everything, trying to hold you up, and that was friction. Okay, that's your FBD. If you got that, then the rest of this problem is actually pretty simple. Okay, now we got two directions we got to analyze. First, we're going to analyze the vertical direction. There is zero acceleration in the vertical direction because that person is not accelerating up nor down. You don't want them to. That's the whole point of the ride. So if we do net force in the y direction equals ma y, well, that's going to be 0 because there is no vertical acceleration. We'll just, for the sake of argument, we'll say up is positive. So in this case, we've got friction minus mg equals 0. Now I'm going to do a little more algebraic work here. What's the equation for friction? Well, it's mu times Fn. And I'm going to move the mg to the other side, so that equals mg. Now, which kind of friction are we talking about? Static or kinetic? Well, a common misnomer is to say, oh, it's kinetic friction because there's motion. Well, there better not be motion. In other words, there better not be relative motion between the passenger and the wall. If there is, that means that passenger is sliding, and that's not good. So it turns out that that passenger is stuck to the wall. So this is static friction. Okay. So we got an equation. Again, we're trying to find velocity. I don't even have velocity in this equation yet, but this is something you have to do to get to the answer. Okay, the other direction we're going to analyze is the radial direction. We always call toward the center of the circle positive. So in this diagram, that's going to be here. There is an inward acceleration or in this particular diagram, a rightward acceleration. That's radial acceleration. Again, that passenger is constantly changing their velocity, not their speed, but their velocity. Their velocity is changing because velocity is speed and direction. And because they're turning, the direction is always changing. And of course, you feel it. Whenever you turn, you feel that acceleration. So if we do net force in the radial direction equals MAR, what's the only force in our radial direction? It's Fn. So we got Fn equals m, and then A in the radial direction is v squared over r. Aha! There's our velocity, okay? So we got two equations, and we're trying to solve for v. I want to get rid of Fn. So in this equation, I'll solve for Fn. So that equals mg over mu sub s, okay? And I'm going to sub that in right here, okay? So we got mg over mu sub s equals m v squared over r. Well, you may have noticed m drops out, okay? So it doesn't matter if it's a little kid or an adult. When the engineer designs this ride, they do not have to worry about the mass of the passenger, which is a good thing. And you're solving for v, you're trying to get it by itself, so you multiply both sides by r, you square root, and you get v, this is v min, okay, would equal root gr over mu sub s. So that would be your equation for v min, and then you could plug in whatever they give you for r and mu and get an answer, okay? Now, and again, notice that mass canceled out, doesn't matter. So it's a pretty easy expression, but again, what we're looking for is, do you know how to get there, okay? Do you know how to analyze the two directions of motion? Here we got the vertical direction where we know acceleration is 0, and then we have the horizontal / radial direction. We know there's a radial acceleration. There's the expression for it, okay? Now, the one last thing I want to mention about this problem or work on really quick is, well, first of all, this is v min. You can go faster than this, but this is the minimum you go. If you go any slower than this, you actually begin to slide down the wall, and that wouldn't be good. If you're going v min, what's the time it takes for you to get around the circle? Okay, we could probably fit that in right here. So what's the period? Okay, well, velocity is 2 pi r over period, or period is 2 pi r over velocity. And here's our v min. So the period is 2 pi r divided by root gr over mu sub s. Now you can do a little math here. You can cancel the square root of r, put that up here, and then the mu sub s goes up there. So t would be 2 pi root, mu sub s goes in the denominator, a root r is in the denominator, and then you got a g down here, okay? So let me just double check that makes sense. Yes, okay, so there is your equation for period if you're going the min velocity. Now, one last question. Now, let me just check that, make sure I've given you the right stuff. I sure am. Is that the minimum or the maximum time to get around? Well, remember, if you go any slower, you're going to fall down. So this turns out this is actually the maximum time. You can take that long to get around or less. You can go faster than that, you just can't go slower. You can't take more time than that. So I hope that was helpful, and thank you very much.